Okay, everyone. Bismillahirrahmanirrahim. Welcome back. And now here we are with another lecture on the combination circuits. So, what will we learn today? It will be just be a bit of review of adder circuits, and we'll build another combinational circuit that is basically your arithmetic and logic unit. This ALU, or in short, it's called ALU, which is one of the most important components of a computer. So, what's the roadmap so far? Where we have been, we have studied about Boolean algebra. We saw the basics of different gates, the digital logic gates. We studied about the Boolean algebra and K-maps, the few techniques to simplify the expressions, to design circuits, the digital circuit, which have to be very optimized. So we studied different circuit design techniques as well. In addition to the using the K-maps or Boolean algebra for simplification, we studied about multiplexer based design, we studied about decoder based design, and we also, in the last lecture, we studied about few circuits about on the arithmetics. We actually designed an adder and subtractors logic circuit using different techniques of digital logic circuits. So what's up ahead? The next today we are actually going to design another arithmetic circuit to wrap up this part of this course. So let's build an arithmetic logic unit. So what's an arithmetic logic unit? Actually, then the name is not strange for you. This is whenever you talk about computers, this ALU is actually the main part of computers. So for you can say that this ALU is actually the heart of a processor. You could say that everything else in the computer is just there to support the ALU. Basically, ALU is something that does most of the processing inside a CPU. So today we'll learn how you can build your own ALU. We'll see how an ALU, a simple ALU, can be built using different operations. We explain how several basic operations can be implemented using just an unsigned adder, a simple adder. You can use that adder. You can simply use that adder to actually perform different operations. Then we'll talk about logical operations and how to build a corresponding logic unit circuit, and then finally we'll put these two pieces together to actually integrate into a ALU. So back to the same adder subtractor again, the same adder circuit that we use to design to do both the addition and subtraction tasks. So an arithmetic unit is a circuit that supports several different arithmetic operations, and the basic one, the most basic arithmetic unit we have studied in the last lecture, when we saw when our circuit actually supported two main operations, that is addition and subtraction. So that circuit has basically that was a 4-bit adder and subtractor. So that circuit had 4-bit data inputs x and y, and a function selection input sub that actually selected either to do addition or subtraction. If the sub value is 0, the operation that our circuit was going to do was addition, and if sub is 1, the result, if the sub is 1, your actually result and the operation performed is simply the subtraction, and we studied how it is done. So hierarchical circuit design, the circuit is basically simple 4-bit unsigned adder which always output the sum of its inputs, and the sum is basically a plus b, the two inputs, plus the ci, the carry in. So technically this adder is basically a simple adder that performs addition of the two inputs A and B. The 4-bit input basically it's a 4-bit adder, so it performs the 4-bit addition of A and B, A plus B, and there is an input CI, so it actually simply does the addition of A plus B plus CI. So to perform the simple addition or subtraction, all we did was just vary the inputs A, B and Ci according to the arithmetic unit inputs X, Y and sub, and basically to do the subtraction we use the sub equal to 1, and the operation was performed was x plus y complement. We use the exclusive OR gate to complement the second input y. Instead of using simple y, we use the complement values of each bits of y to get the simple ones complement, and the CI was connected to sub to make it 1, so that the actual operation that was performed was x plus y complement plus 1, which is actually the same thing as doing the x plus y complement plus 1 is basically the 2's complement of y, so we can say that x plus 2's complement of y, which is the same thing as x minus y. So this is the basic concept of a simple adder subtractor circuit, and this will be very helpful for our ALU design. So some more possibilities, what more we can do with the same adder subtractor circuit, a simple 4-bit adder circuit. What more we can do, we can actually, here are a few examples of the more possibilities. S is equal to x, simply transfer function. Basically it's a simple buffer, or you can say you can transfer x into output. How can it be done? You can simply add with a 0. So basically adding with a 0 will result in the same number, so it's just a simple x transfer. We can actually do the increment. How to do increment is basically addition a number plus 1. So we can do this by just using the carry input Ci input as 1, with 0 as the second input and x as the other one. So you are just doing x plus 1 because Ci is 1. So this is a simple increment. And similarly we can do a decrement. How to do a decrement? We'll just add a -1 to the original number. So what's a -1? -1 in simple terms, in a 4-bit number, all ones will correspond to -1. So if you just add a number with all ones, it's basically adding it -1 to that number, because it's the 2's complement of that already. So if we are just doing the addition with all ones, it's basically subtracting 1 from that number, so it will be a simple decrement. So transfer the same x output, or increment and decrement, these can be added to your main adder to get these operations as well. So the role of Ci is very important. Notice that for the transfer and increment operation, the adder has the same A and B inputs, and only the Ci input differs. You can see here the A is 0, B is x in both of these two cases, where x s is simply transfer or increment. Both the cases the result is actually a little different because Ci is different. When Ci is 0, it's simply x transfer. If Ci is 1, it means we are doing a increment operation. So in general, we can always create additional function by setting up Ci is equal to 0 instead of Ci 1, and vice versa. So Ci is basically the main thing. If we can use different values of Ci as 0 and 1 and do different operations according to those values. So another example involves subtraction. We already know that the 2's complement subtraction is performed by setting A is equal to y complement, B is equal to x, and Ci is equal to 1. So the adder outputs x plus y complement plus 1, the same thing I just told you about. So the second input, if we keep A is equal to y complement and B is equal to x, but Ci to 0 instead of 1, which is actually the A minus 2's complement, basically 2's complement subtraction, A plus x minus y because that y complement plus 1 is negative y according to 2's complement. So if we just use ci equal to 0 instead of ci 1, it will be simply x plus y complement, and this turned out to be a 1's complement subtraction. So we are just doing the subtraction. It will be the 1's complement subtraction. That may not be the most efficient one, but it's the step for 1's complement subtraction. Okay, here we are, the table of your ALU that we are going to design today. So here are different arithmetic operations that actually we have seen today. You can see here, and how we can implement these using the same adder. So here we are, x and x plus 1, the two operation when we change the value. If we use ci is equal to 0 and a as all zeros, so it means this is the, if we keep ci is equal to 0, it will be x plus 0. The result will be simply x plus 0, which is the transfer. And if we use ci is equal to 1, it will be x plus 0 plus 1. That means x plus 1, we are doing the simple increment operation. The second one, if we use simple y without doing the complement, the same, if we take y as input to a, so that will be a simple addition, x plus y. If we keep ci is equal to 0, it will be x plus y, and if we do ci is equal to 1, it will be x plus y plus 1. So that is another operation that can be done by changing ci values. So x plus y plus 1. Similarly, if we use y complement instead of y, then now as a, so it will be the two different operations will be x plus y complement, a simple 1 complement subtraction, and x plus y complement plus 1. That is the 2's complement subtraction, and the real subtraction that we use in the circuits, that will be x plus y complement plus 1, the 2's complement subtraction, by just keeping ci equal to 1 in this scenario. And similarly, if we do the all 1, that's a, that is actually negative 1 of the 2's complement of 1, that has a value of negative 1. So if we use ci equal to 0, it will simply be x is equal to x subtraction. It will simply be x minus 1. It will be a simple decrement operation because you are adding x plus negative 1. And if we keep ci equal to 1, it will actually cancel out this minus 1 stuff, and so it will just be a simple subtraction, and x minus 1 plus 1 will be the actual operation that's going to be performed using this scenario. So you should notice that the transfer function, the simple transfer function, can be implemented in two ways and appear in the table twice, one for simple increment, one for decrement. So these are the things that can be done. Okay, the next thing, we can make a circuit to actually generate the input a. That is actually different. So we can actually use the 3-bit selection code for each operation. So we can specify which function should be computed according to the selection code. So we have got a 3-bit selection code, 000 to 0 all ones, S0, S1 and S2 are the selection bits that actually decide which operation it's going to be performing. So for x transfer and increment, it's 000 and 001, and similarly 010 and 011 for addition, 100 and 101 for subtraction, and 110 and 111 for decrement and transfer. So here you can see actually there has to be some scenario where we actually set up the inputs to the main adder according to our selections. So the circuit, there has to be a small circuit that actually generates the inputs. The circuit for arithmetic unit just has to generate the correct input for the adder. based on the value of x, y, and s. So you can see from this table here, you can simply use s0 as ci. Ci is just the same thing as s0. Whatever the value of s0 is, ci is the same. So the added input ci should always be the same as selection code bits s0. The added input b is always x. We can see here b is always x, so we don't need to change anything for b. B is simply x is directly connected to b. But what happens to a? A is something that depends on the different thing. A basically depends on y. A depends on s1 and s2. If s1 and s2 are 0 1, it means a is y. If it is 1 0, it means a is y bar. And otherwise, if both s1 and s2 are 0 0, it means a is 0. All a's are zeros and all bits of a are 0. And if s1 and s2 are both 1 1, it means all bits of a will be 1. So there has to be some logic that we need to design for generating this input a. So that input logic has to follow something. So here we can see some things. Ci is already connected to s0 and b is already connected to x, so these two are already fixed. Then the rest is a. For a, we have to follow that code. We know that if s1 and s2 are both 0 0, it means a is all zeros. If it is 1 1, it means a is all ones. And for 0 1, it is y, and for 1 0, it is y complement. So this is how your a input going to be generated with this simple input logic. So we'll build this circuit, but here's another common thing, that actually we have to generate the 4 bits a0, a1, a2, and a3 for output. But one thing is actually common here. All the 4 bits you can see here, they are actually these a3 is actually the same reflection of y3. So if we are using this scenario, when the a is exactly y, that means the y3 will be exactly going to be transferred into a3, y2 will be transferred to a2, y1 transfer to a1, y0 transfer to a0. So the logic of actually generating a from y is going to be the same. Similarly, if a is 0, it means all a's will be 0, so we don't need y here. And if a is 1, it means all bits of a will be 1. If we are going to transfer either y directly, so every corresponding bit of a will be actually reflection of y3. Either it will be directly y3, or it will be the complement of y3 in transfer to a3. So if we have y complement, it means a3 will be y3 complement, a2 will be y2 complement, a1 will be y1 complement, and a0 will be simply y0 complement. So it means each a output is basically the same function of the corresponding bit of y. So it means we just need 4 replicants of the same function that is used to generate the function a. So from this table, this is basically the simple table that is expanded to a proper 3 input table, because y is your input. If y is 0 and 1, y is 0 1, basically for each y input y bit, you can see if y is 0, for s0, s1, s2 0 0, it means your a will always be 0 whatever the value of y is. If y is 0, still a will be 0. If y is 1, a will be 0. Similarly, for s1 and s2 both 1 1, in the last case, you can see whatever the value of y is, the a will be unchanged, it will be the same one. And for the middle two, if s2 s1 are 1 1, sorry 0 1, so it means the y value will be directly transferred to a value, because you can see here that for 0 1, the a is exactly y. And for 1 0 you can see is basically the y complement. So whatever the value, if y is 0 the a will be 1, if y is 1 a will be 0. So this will be the function for your input function for for a, where ai is basically from this simple table scheme map. You can see here that this ai is basically s2y complement plus s1y. So this will be a simple two-level circuit using two AND gates and one OR gate to generate each bit of a from your y input. And again we have to repeat this one for each other input a3 to a0. So it's actually the same circuit repeated 4 times for this input logic. So this is your input for your a, and the rest is the same. This is your complete arithmetic unit for all the operations, all the inputs specified. Here's the block diagram for you: 4 input x, 4 input y, because x and y are both 4 input 4-bit inputs. So and we have got 3-bit select signals, and the selection code S0, S1 and S2, and those selection code decide what to do. For 000 it's going to be simple x, for 001 it's x plus 1 increment, then x plus y plus 1, that we actually saw in the last few slides before. This is your complete arithmetic unit. So arithmetic unit is the first part of your today's agenda. So now we'll see how your logic unit is designed, and we'll integrate both of them in the last. So logical operations. So arithmetic operations were done. Logic operations are basically much simpler than your arithmetic operation, and they are just and logical operations are actually a bit different as well, a bit diversity in logical operations. Basically what we'll be doing, or what's done in your computer, the ALU, it's called bitwise logical operation. Why it's called bitwise? Because each bit of the number, the actually operation is performed by the corresponding bits for your each number. So these are called bitwise logical operation. For example, here we have got 3 logical operation: AND, OR, and exclusive OR. These are the 3 basic logical operations, but we are doing the bitwise logical operation. Bitwise means each corresponding bit, the operation is performed between the 2 corresponding bits for each operation. So here we can see the bit number 0, 1, 0, 1 and 0. The AND operation is done between these 2 numbers, a1 and 0, because we know that AND needs to have both inputs 1 to make output 1. So it means 0 and 1, and between 0 and 1 will be 0. So this is your AND operation, bitwise AND operation. 1 1, the bitwise between 1 1 will be 1, bitwise between 0 1 will be 0, and bitwise AND between 1 1 will be 1. So this is your bitwise AND result of 4 bits of these 2 numbers. Similarly, bitwise OR will be the OR operation that's for the corresponding bit numbers for the input numbers. So you can see here 1 0, the bitwise operation between 1, OR operation between 1 and 0 will be 1, and you can see all the bits are the OR operation are done according to the specific bits. And the third one, exclusive OR is actually a little different. We know that if exclusive OR, if the both numbers are same, the result of exclusive OR will be 0, and if they are different, the result will be 1. The same thing we actually studied in the subtractor design, when we used an exclusive OR gate to get the complement, because if we have a 1 here, if we are doing the complement with 1, the exclusive OR with 1, the result will always be the complement of that number that we can see in the middle 2 bits in this scenario. Right, so these are the few bitwise logical operations that we'll be doing here. So bitwise operation, they are not new for you because you are computer science students. You must have seen the different languages in your programming courses. You must have used the bitwise operation operator there. There are actually two different types of logical operation that I just told you about. The bitwise operation is like the when you do the operation, every corresponding bit will do the operation will be done on the corresponding bits. And these are the bitwise operators which are used in these programming languages of C, C++, ampersand for and, simple pipe symbol for or, cap symbol for exclusive or, and a symbol tilde for not. So these are the common symbol for different operators in these languages. So simply 13 ampersand 25, that means 13 and 25 will result in 9 because each bit generates the corresponding bit value for as output. The operation is done on the corresponding bit and the result is shown as the output. And we know that these bitwise operations are not the same as the logical operations which are actually denoted by double ampersand, double pipe, or symbol not symbol, the sign of exclamation for not, which treat each integer as single logical value. So here if we are doing this operation 13 ampersand 25, that means we are doing the logical bit logical operation logical operation here. So 13 and 25 will result in simple one because the one here means true. So every non-zero value will be treated as a true value. So because true and true will result in a true, so the result is one. So it will only result in zero if we are doing the ampersand operation with zero. So similarly, bitwise operation is also used in networking. If you have already studied a bit about networking, it's actually very handy. These operators are very handy to generate the subnet addressing using subnet masks. So simply AND operation is used to generate the exact network addresses, and to generate broadcast addressing. An OR operator is used for that. So you see it more in your networking as well. So I'll not go in detail. So okay, here we are. Let's see how we build a logic unit that perform different logical operations. A logic unit implement different logical functions on two multi-bit input x and y. We have got the similar scenario just like arithmetic unit. You've got two multi-bit inputs. We can build a simple 4-bit logic unit just like a 4-bit arithmetic unit, but this time it will be logical function. We'll design this 4-bit logic unit that supports 4 operations. Which 4 operation? A simple AND operation, an OR operation, an exclusive OR operation, or a simple NOT operation on X. So we'll have to assign a selection code just like your arithmetic unit to select between the 4. So for 4 operations we need a 2-bit selection code, S0 and S1, 2 bits, that will select the which operation it's going to perform. So implementing bitwise operation is actually much more simpler than your implementation of arithmetic unit, because it's a simple bitwise operation between two numbers. So every corresponding bit of each number are basically the bitwise operation is performed on those bits. So that bitwise operation is simply implemented using that specific logical gate, and that can be selected as output. So we can implement each output bit gi as shown on the right on this figure. You can see here using that specific gate for here for 0 select code. So that select code is actually used as input of a multiplexer that will decide which of the input is actually going to be selected as your final output. So which operation is going to be selected? that will be decided by the select code. If the select code is 00, it means the 0 input, that it's a simple multiplexer. So 0 input is basically an AND, the output of AND operation between xi and yi, the bitwise AND operation. For D0, bitwise OR operation for D1, bitwise exclusive OR operation for D2, and bitwise NOT operation for D3. So these are the 4 operations that are done. This multiplexer select one of these operations to be selected as logic unit, which is performing 4 different tasks, different operations, and a multiplexer is actually used to select one of those operation output as your final output of this logic unit. For a 4-bit number, we need to use the similar settings 4 times. So this is your same scenario, same module, the same multiplexer with 4 different operation and gates as input of those multiplexer. We use the same multiplexer 4 times to get your whole 4-bit logic unit. So that logic unit will have 4-bit X, 4-bit Y, and 2-bit select signal selection code of 2-bit to select which of the operation is going to perform, and 4-bit individual gate, because it's a bitwise operation. So these are just the output of individual gate operations for each bit. So this is a 4-bit logic unit that performs AND, OR, exclusive OR, and NOT function on input X. So next thing is now let's see how we combine the both of these, arithmetic and logic unit. So we can combine our arithmetic and logic unit into a single arithmetic logic unit that is going to be your main final design. So the ALU will accept 2 data input X and Y, the same X and Y for arithmetic unit and same X and Y for logic unit, and a selection code S. That selection code will be a little different because both arithmetic and logic, they're not using similar type of code. So the output will be G, that will be general output G, and a Cout as well. Cout will be used only for addition, the arithmetic operation, arithmetic unit only, will not be used in logicals. So that will be another output. Since there are 12 total arithmetic and logical operations to choose from, we need a 4-bit selection. Why? Because there are more than 8, so we need 4-bit selection code, which is going to be S0, S1, S2, and S3. We have added a selection with S3. This will be your main to choose between an arithmetic unit and a logic unit. So for logic unit we just need 2 bits for selection, and for arithmetic unit we need 3-bit for selection. So the final output will have a selection 4-bit, and this S3 is just going to select either from arithmetic or logic unit the output is going to select from. So this will be a complete ALU circuit. This will have X and Y, the 4-bit X and Y going to both these arithmetic and logic units. The S0, S1, and S2 are there. So from here you can see the S0 and S1 are actually used for logic unit as well, and along with S2, S0, S1, and S2, they are used for arithmetic unit. So we can use S0 and S1 for both arithmetic and logic unit. S2 will be used only in arithmetic unit, and S3 will be used both for selection. So S0 and S1 are only going to logic unit. S0 and S1 and S2 will be the selection code for arithmetic unit, and there will be another selection signal S3 that will be deciding which output is going to be viewed as the final output. So there will be a quad 2-into-1 multiplexer at the end that will select either the output from either of arithmetic and logic unit. So it's going to be very simple. Cout should be ignored when logic operations are performed because it will not be used for Cout. for logical operations, but in arithmetic it will be used. So S3 is going to select from the two output of arithmetic and logic, and that will be done by this final multiplexer. So about the multiplexer, both arithmetic and logic units are active. This is actually the main property of combinational circuits, that all the outputs, all the units are already generating outputs. So it means whether we are using an arithmetic operation or logical operation, the output of both the systems are actually there. So which output we need, we have to select from this multiplexer. It means both of the outputs are already there. So that's why you use a multiplexer. In programming, you use an if then else statement to select the one operation or the other. This is actually useful in programming. You can also make a relationship between a hardware design and a software approach. It's basically multiplexer is just a simple if else design. If if else statement in a typical programming language is actually the same thing as a hardware. Secondly, our hardware scheme may seem like a wasted effort because both of these are already producing output, but we are not using one of the outputs. But it's not really that wasted effort, because disabling one unit or the other would not save that much time. We have to build the hardware for both units anyway, so it's not something that's overkill. So we can think of it as a form of parallel processing where several operations are done, but some of them are selected. Here in this scenario, both of the operations are done, but only one of the output is selected. So this is actually very common example of actually application of multiplexers, and that is used. Multiplexers are used for the same purpose in the logic design. So this will be the final external view of the ALU. ALU will have 4-bit X, 4-bit Y, and a 4-bit selection code that will generate the output G. G will be the output, and a C out will be another output that will be for arithmetic only, but it will be an output of ALU. And we have the whole table to get the different functions listed in this table. So here it is. We just build a simple ALU to design to implement few basic arithmetic and logical operations. So let's just wrap it up. This was actually your last lecture about the combinational circuits. We have learned about the combinational circuits. We saw how you simplify the expression logic, Boolean expression using different techniques, using Boolean algebra, using K-maps, and we also studied about design how to make efficient optimized circuits using different tools. We also use decoders and multiplexers in our circuit to design better solutions. And in this lecture we actually designed the whole ALU, a complete working ALU that does work. So this was about combinational circuits. Next up is going to be sequential circuits, where the circuit is actually held up for some time. So time-based synchronization is going to be what you learn next. So get ready for that. And until then, Allah Hafiz.